All right, we're recording. We're rocking and rolling. That's great. All right. So, now you finally get to just listen to me. Perfect. Thank you. All right. Where are we here? Things are a bit sluggish, but we'll get there in the end. All right. Hello. You guys, math 114, 002. Oh, all right. So you can, oh, come on. I don't know how long it takes, but that should be good. Find me on YouTube. Search Emily Lee for fun lecture videos. Nice. Yeah, I'll be YouTube famous in no time. Yeah. Well, I mean, I guess technically I am. I'm paid to be here. So I'm already a YouTuber, I guess. Cool. Yeah, so I had to kind of find a workaround for the Slack because Slack wasn't working, and so we're ditching that completely. Going to be in Moodle, and so say that again. Yeah. Will I read them? Probably not. I doubt it. I highly doubt it. Unless they're all flattering, then I'll probably read them every now and then. But otherwise, probably not. But they're there. You'll have them, and of course you'll have these notes just as PDF on Moodle. Okay, so we'll be on Moodle. I'm bummed about the messaging aspect that we're missing out on, but oh well. Yeah. Email's so boring. Feels clunky somehow. Okay, so we won't do any review, mostly because, well, I wasted a lot of time. So here we go. A lot of what we did last day is going to be covered here. So today we're starting section 2.3. Hey, stop talking. Back there. Thank you. Linear programming. Linear programming, it's all led up to this, right? So everything that we've done so far in the course is going to be incorporated into this one thing, right? Do you mind closing the door back there? Cool. Thanks. It goes from you guys being loud to being quiet, and then the hallway gets loud. I just can't win here. So we've all built up to this, right? This is where we put all our skills into play. Okay, linear programming is for more realistic situations, right? So last day we talked about just functions and solving systems of equations. And so now we're going to be dealing with a profit function, right? So a profit function, which we want to maximize our profit, right? That sounds like a good idea, right? But a lot of the time we're going to have restrictions, right? We only have so many labor hours, for example. We only have so many hours in the day, right? We can only produce so much, right? Maybe we have a limited amount of materials, right? And so linear programming is a way to take into account all these restrictions and maximize our profit, right? So to say, well, we should be using this much material in this many hours, and that'll maximize our profit, Pretty fun stuff. So we often have restrictions on our profit function things like, things like time, materials, machinery, maybe. Machinery, even labor, right? List goes on, but those are some common ones, okay? So linear programming, we said, is gonna let us maximize our profit function. So linear programming will let us maximize a profit function given a set of restrictions. A set of restrictions. Okay. For example, so I'll kind of lead you through it by example, and then we'll go through the general kind of steps of doing it. Okay. It is a really involved question, but it will be on the test, right? And so it is going to be a big part of test 1 because it does test all the things that you've learned so far. Yeah. Does anyone have that term schedule I gave you?
Yeah, week 5 on October 4th.
October 4th? Cool. There you have it. But we'll do a review day before, so where we go through the practice test together. So just as a quick mini example, so if I tell you that the profit of X, right? This is a profit function. So the profit of X is going to be 3X plus 4Y, right? So we have X and Y representing some thing, right? Time and materials maybe, or yeah, things like that. Machines available, material, right? It doesn't matter. And then I tell you that the restrictions are that X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. This is kind of a default because if we're talking about things like time or the amount of labor that we use or the number of machines, right? We can't have negative values for any of these things, right? So very often, just your X and your Y, regardless of what they are, have to be bigger than 0, right? But we say them just to be complete, okay? And in a simple form, I might say that X has to be less than or equal to 4, right? So we also can't have more than 4. Of X, and same thing for Y. Y has to be less than or equal to 4. Okay. Just as a little side note, right? This is greater than or equal to the less than or equal to. If you make an L like less than, right? It makes a less than. So you just read it as X is less than or equal to 4. Okay. So those can be hard to keep track of, but less than, oops, or equal to. Okay. All right. So as a fact, if we want to maximize the profit function, right, taking into account these restrictions, we have to map out the set, so the feasible set, which is the area that satisfies all those restrictions, right? So if we imagine, we know that y has to be greater than 0 and x has to be greater than 0. Right? So we know we're working in the top right-hand quadrant, right, the first quadrant. And so, and then we're told that x has to be less than or equal to 4. So here at 4, we have to be on this side. Right. And then at y equal to 4, let's just pretend it's here. Right? Y has to also be less than or equal to 4. So we're kind of down below it. Right? And so now, right, we can draw a line here and a line here, but the feasible set is going to be this area here. Feasible set, right, is all the XY combinations, right, that satisfy the restrictions. So all XY combinations that satisfy the restrictions. Okay. So in theory, right, we should be trying all those XY combinations, right? There's an infinite number of points, technically, right, in this little area, this 4x4 square. Okay. But as a fact, the profit will be maximized at one of the intersections, right? So at one of the extreme points of the feasible set. Okay. So as far as our intersections go here, right, we have our first intersection down here at 0, 0. Right? We'll call that A. Our second intersection, right, or I'll just write 0, 0. At B, B is at 0, 4. Right? X is 0, Y is 4. Let's call this C, 4, 4. And finally D, 4, 0. Okay. So using this coordinate notation. Okay, so little fun fact. An LFF, a little fun fact. The profit function will be maximized at one of the points of intersection. At one of the points of intersection. Oops. That's great. Right? So one of those points is going to maximize our profit function. So later we'll see that it's not always going to be this easy, right? And that's why we had to develop how do we solve a system of equations, essentially solving for a point of intersection, right? Because we're not always going to be able to look at it and say, oh, that's at 4, 4 and 0, 4 and 4, 0, right? So that's where we're headed, right? And so, but for now, right, the profit function is going to be maximized at one of these points of intersection. Okay. So what we do is we make a table of all these ordered pairs, so all the points of intersection, and then we evaluate the profit function at each of those XY combinations. The highest profit there, that's where you're maximizing your profit function. Okay. So now we make a table of the points of intersection and evaluate the profit function at each XY combination to find the maximum. So we make a little table. I'll put here the intersection. A was 0, 0. B was, and this is why I like to label them, right? Because then we can talk about those points, right? A, B, C, D. Okay. B was what, 0, 4. C was at 4, 4. And D was at 4, 0. Notice that we haven't actually looked at the profit function. We haven't considered it at all until this point, right? So that's one thing to keep track of, right? You're going to deal with your restrictions only for a long time, and then you bring in your profit function. So you don't try to incorporate it in your earlier calculations, right? But we were told that the profit was 3x plus 4y. Profit of x was 3x plus 4y. So then for A, point A, we have 3 times 0 plus 4 times 0. That's just 0, right? I can almost guarantee that 0, 0 will never maximize your profit function, but it's always going to be in there. We always have to use it and show it, but it'll never happen. How about point B? So 3 times x is 0 plus 4 times 4. Let's call it 16. That's better than 0. 3 times 4 plus 4 times 4. 12 plus 16. Let's call it 28. That's even better, which we kind of suspected, right? 4, 4 should give us a, it won't always be that obvious, right? But this is a basic example. 3 times 4 plus 4 times 0. 12. So now, right, of these 4, now we just look at our list, 0, 16, 28, 12. The highest is 28, right? And so this is our maximized profit. Cool. So then we write a little note saying the profit is maximized at x equal to 4 and y equal to 4 for a profit of 28 units, right? Whatever. Okay. Cool. So let's summarize this into steps. So that's how we do it, right? But let's, oops, how do we maximize the profit function? Just general steps. Of what we just did. So the first thing we did, right, was draw all the restrictions on the same graph. Okay. So draw all the restrictions on the same graph. Right? And so that is going to give us all the feasible set, as we call it, right? All those, the area that satisfies all the restrictions. Right? So identify the feasible set, right? The area, I'll put in brackets, the area that satisfies all the restrictions. From there, you have to identify all the points of intersection. Okay. Identify all points of intersection. That's right. Yeah. We'll have to solve for them. Yeah. And we'll do a more realistic example once we've gone through the list. So then you'll see. Yeah. But you will have to I'll put in brackets, solve for points of intersection, potentially. Solve for points of intersection. Okay. Which could be some work, right? Once you have all your points of intersection, right, then we make a table of all those points and we evaluate the profit function to identify the maximum. Right? So make a table of all the points of intersection and evaluate the profit function at each point to identify the maximum. Cool. Pretty involved, right? But let's do a little example, or a little bit bigger example, I should say. Shouldn't call it little. It's pretty big. Any questions though before we get started? Oh. No, there could be more. Yeah. In fact, 1, 2, 3. No, there's 4, but they're wonky. But yeah. We could have more than 4 points. Okay, so we're doing example 72, and we are asked to maximize the profit of x is x plus 1.2y. Subject to, right, so these are your restrictions, subject to 2x plus y is less than or equal to 180, and x plus 3y is less than or equal to 300. And then x is greater than or equal to 0 and y is greater than or equal to 0. Those last two are kind of gravy, right? We assume those almost, but we have to say them. So I used to really hate dealing with inequalities, right? Less than, greater than, that kind of stuff. But you can treat these as equal signs, and eventually we will just start treating them as equal signs, right? All it's saying is that if the restriction is that 2x plus y has to be less than or equal to 180, right? Then we can draw the line of 2x plus y equals 180, right? And then everything below it satisfies that restriction, right? And so that's what that inequality is saying. So we still draw the line with the equal sign in it, right? But the restriction is everything below that line, right? So you can treat them as equal signs as long as you remember to switch the sign if you happen to multiply or divide by a negative number, right? Only multiply and divide. Okay, so let's make a little note of that. So we can treat the less than or equal to or greater than or equal to as an equal sign. But if we multiply or divide, both sides by a negative number, the sign will switch direction.
So instead of being less than or equal to, it turned to greater than.
That's right. Yeah. So we just switch from whatever it was to the other one. Okay. So we learned last day, right, how to graph lines. So now this is an equation of a straight line, right? 2x plus y equals 180. X plus 3y is 300, right? Each of those only have an x and a y, so we can rearrange them into the form of y equals mx plus b, right? And so we'll label this one, I'll call this equation 1 and this equation 2. They're the only ones we're going to be concerned with for now, right? Because step 1, remember, is to draw the restrictions on a graph, right? And so we got to do that. So we have to draw these two restrictions on our graph. Okay? So I like to start by solving each of these for y, right? Getting them into the form of y equals mx plus b. Right? So solve 1 and 2 for y. Equation 1 was 2x plus y is less than or equal to 180. Okay. Solving for y on one side, I can just subtract 2x from both sides, so I get y is less than or equal to 180 minus 2x. We only switch the sign if we're multiplying or dividing, right, by negative. Okay. Great, so essentially we have y equals 180 minus 2x. That's great. Okay. So now let's solve for y in our second equation. So our second equation was x plus 3y, is less than or equal to 300. Solving for y, right? We have to subtract x from both sides. So that puts us at 3y is less than or equal to 300 minus x. And then we're dividing by 3, right? Both sides by 3. So we get y is less than or equal to 300 minus x over 3. No, because we were dividing by a positive number, right? But if we had -3, right, and we had to divide by -3, then yes, you would switch it. Good. Good, good, good. So, fractions. I know, guys, I know. You could solve for x. There's nothing that says you have to solve for y. I just like to get it in the form of y equals mx plus b, but yeah, it doesn't matter. So we did this last day, right, where we had to break up the common denominator to get two separate terms, right? It's just nicer to deal with. So we have y is less than or equal to 300 divided by 3 minus x divided by 3. That's also why we can't just cancel the 3 in just the 300, right? Because x is also being divided by 3. That's a pretty common illegal math move that I see, right? Where I say, oh, 300, oh, I can just cancel the 3. Great, done, right? That's not true. Yeah, because it's still x over 3. Don't worry, you weren't the only one. So 300 over 3 we can reduce to 100 minus x over 3 can't be reduced anymore, right? So even though it's a little bit ugly to look at, that's what we have. Yeah.
Do you mind if we went from the first equation unsolved to like the last one?
You don't have to show all the steps, but I do want to see, this one and this one. That would be enough. Or something kind of similar. Cool. All right. So, great. The whole goal is to draw these lines, right? We spent last day talking about how do we draw lines. We have to find 2 points on each line, connect them, extend the line, right? And so to graph 1 and 2, we need to find 2 points on each line. Technically at least 2 points, right? But I only ever do 2, so that's okay. We need to find 2 points on each line. Here I'm going to switch to y equals 180 minus 2x. Because remember, the equals is just that line that we're drawing, right? And then the less than or equal to is everything below it, right? So let's pick some nice values of x. 0 is always nice, right? So we get 180. And another nice value of x, because we're dealing with 180, which is a pretty big number, right? Let's pick a larger value of x. Sure. Or how about 50? Just because because I want to. So then we have 180 minus 100. Just making a list here of our x, y pairs. We have 0, 180, and 50, 80. Right? You don't have to do that, but I like to have them available. Okay. How about equation 2? Right? We have to pick x values again. Y equals 100 minus x over 3. Again, x is 0 is really nice to deal with. Right? Gives a y of 100. Right. Now let's pick a nice value of x, right? Something divisible by 3, perhaps.
Why do we use different values in the same one?
We can pick whatever values we want. So you can use the same one if you want. Yeah. Sometimes some values will be nicer in some equations than others, right? So for example, well, the first equation is really nice and clean, kind of 2 times whatever works, right? But if you had fractions in both of them, right, you might want to pick and choose. But yeah, the key thing to remember is you can pick any value of x that you want. Yeah, so in our case, right, x has to be greater than 0, so we use only positive x's. But so let's pick, I've got 30 here. 30 is nice and divisible by 3. That's that 90. Right. So we'll just make a little list here of our xy pairs, 0 and 100, and 30 and 90. Cool. So now we're going to plot these. Okay. And so we know that our maximum value of y is 180, right, in our list. And so it's very likely that that's going to be our maximum value, but we have to have room for 180, right? So if I make each page line worth 20, right, I need 9 lines. So just so you can plan out your plot. Okay. Let me see if I can make this little grid work. Woo. Okay. How many was that? 1, 2, 3, 4, 5, 6, 7, 8, 9. Hey, great. So I'm cheating. Of course, on the test, I'll give you the grid, right? So this is kind of work that we wouldn't have to do, right? So I'm just gonna go here, and I'm making each line worth 20, 40, 60, 80, 100, 120. Thank you. 160 and 180. Okay. Same thing on this end. 20, 40, 60, 80, 100. I'll go to 120. Just because I know I don't need to go past 120. But like I said. Pardon?
Just maximum value for the x is just 50.
Well, we'll get there. Yeah. Oh, in the values that we used, you mean? Here? Oh, yeah, but the lines are going to extend. Right. Yeah, but otherwise, yeah, you could stop at 50 and then realize, oh, I need more. But yeah, totally. Okay, so let's plot these points, right? So for line number 1, we start at 0, 180. So I'll just do a different color here. 0, 180. And then I think we said, what, 50 and 80? So 50 is going to be somewhere between 40 and 60. Somewhere halfway. Right, so here we have 50, 80. And then now we take whatever straight edge we have available, right? And we just connect the dots, draw our line, and extend it to cover our graph. Right? And so, and like I said, in the test, if you just kind of take the edge of your paper and you kind of just fold it over and use that as your straight edge, that works too, right? So you don't have to be bringing rulers or anything crazy like that. Let's see if I can pull this off. Nice. Yeah. So I'm just going to label my line here that this is line number 1 at y equals 180 minus, is it 2x? Yeah. And now, right, we know from our inequality that everything below this line, right, that's going to be this area here, right, is going to be passing our restrictions. I'm going to undo that because we need to draw our second line. Right? So let's get our second line on here. 0, 100 is our first point. And our second point is at 30, 90. So x is 30, y is 90, some between 20 and 40, and between 80 and 100. Right. So now we can, or I guess I should label it. Now I'm going to connect these dots. Okay. And extend the line. Got confusing, right? Because it's really close to that other dot for line number 1, but you have to keep them separate in your mind. Right? And so this is line number 2 at y equals 100 minus x over 3. Okay. And the restriction was that everything has to be less than this, right? So x has to be greater than 0. So x has to be greater than 0, puts us all the way out here, right? Y has to be greater than 0, so everything about here. Everything has to be less than this line and less than this line. Right? So this is our feasible set, right, as we call it. Okay. So those are all the x, y coordinates that would satisfy our restrictions. Okay. Feels like a lot of work already, right? But now we have to find our points of intersection, right? So we have drawn lines, right? That's from last day. We have to find points of intersection. That's from the other day, right? So like I said, everything just kind of works up to this, right? So we have, let's highlight our points of intersection. And I'm going to label them A, B, C, D again. Right. So A and then B, C. Right. C is neither of those points that we've drawn, right? They just happen to be really close to the point of intersection. Right. And then D is where line number 1 crosses the x-axis. Okay. So we know where A is. A is at 0, 0, right? That's fine. We know where B is. B is at 0, 100. Yeah.
Does like the 180 point have no? Does it come into play?
It's not in the feasible set because it doesn't satisfy that second restriction. Yeah. But good. We know where B is, right? 0, 100. We don't know where C is, right? So we have to solve for C, the point of intersection. And we're also going to have to solve for D, right? The point of intersection. Okay. So we need to solve for C and D. So C is the intersection of, and this is where it helps that we've drawn out these lines. It's the intersection of 1 and 2. Okay. Of 1 and 2. Okay. Remember y, and this is where I'm going to start using just the equals, right? Because the whole point of that inequality, the less than or equal to whatever, was for drawing the graph, right? Now we can just deal with the lines to find the points of intersection. Okay. So y for equation 1 was 180 minus 2x. And equation 2 is y equals 100 minus x over 3. Okay. This is a little bit easier than finding the points of intersection that we did before, right? Because we've already solved for both of them in terms of y, right? So not only is it nice to look at y equals mx plus b, right? But it makes this step much easier because now you can substitute y equals, well, you can pick whichever one you want into the other one, right? Essentially setting them equal to each other because they're both equal to y, right? But following the same kind of methodical way that we have been using, right? We substitute the y from equation, whichever one you want, let's say equation 2 into equation 1. Right? So substitute y from 2 into 1, or 1 into 2 if you want. They'll end up the same. Okay. Bless you. So equation 2 says that y is 100 minus x over 3. And equation 1 says that y is 180 minus 2x. Right. So now we need to solve for x. I want to get my x's to one side and all my numbers on the other side, right? And so I'm going to move my 2x to the left-hand side, right? Because I like positive numbers, right? But you can do either way, right? So I'm going to do it in one fell swoop here. I'm going to have negative x over 3 plus 2x is 180 minus 100, right? Just did a double swap. Right. Okay. So we get, I'm going to rearrange the left-hand side to be 2x minus x over 3, which is nicer to look at. 2x minus x over 3 is 80, right? 180 minus 100. Okay. So we still have to deal with this fraction, right? 2x minus a third x. Okay. I'd say it's the longest, but also the safest way, right, is to convert 2 to something over 3, right? 6 divided by 3 is 2. Right? You can, so technically using cross multiplication here. So we rewrite this as 6 divided by 3x minus x. Oh, you know what? I'm going to write it as 1 over 3 times x. That's the same thing, right? X over 3 is 1 over 3 times x.
I'm confused. I'm lost a little. Can you give us
Which,
arrows and explain it like a pie?
yes.
Yeah.
So, whoop. So we want to get 2x over a common denominator with 3, right? And so we did that before, right? And we said that 2x times 3 over 3, right, minus x over 3 times 1 over 1, technically, right? Because 2x is technically over 1. Right? So we're taking the denominator of each of them and making it 1, right? X over 3, right? The denominator is 3. So multiplying the other term by 3 over 3, right? 2x has a denominator of 1. So multiplying x over 3 by 1 over 1, technically. Okay. Keeping the 80 on the right-hand side. Okay.
Which leads you to 6 over 3 times x.
That's right.
Okay.
Yeah. So remember, the goal here is to collect like terms, right? But because we have the x over 3, the fraction, right, we can't add or subtract fractions unless we have a common denominator. Hey, that sounds like one of these days that we met, right? Adding, subtracting fractions. Like I said, it all comes into this. Okay. So now we can simplify this and say 2x times 3, that's the same as 6x over 3 minus x times 1 is just x over 3 times 1 is just, 3. That was that.
Dividing by x, we just change the whole thing by x?
Yes, they're just hanging steady for now. Yeah. Because technically 2x is over 1. And so if we're doing the same thing to both sides, we're multiplying x over 3 by 1 over 1. So you can see. Okay. So now that we have this common denominator of 3, right? Now we can pull out, so we can factor. Hey, it sounds like something we've done, right? So we can factor out the x, right? We have a common multiple of x. X times 6 over 3 minus 1 over 3 equals 80. And now we can finally reduce these fractions to one fraction. So we keep our common denominator of 3, right? And we just subtract the numerators. So 6 minus 1. So we have x times 5 over 3, 80. Finally solving for x, right? We have to multiply both sides by 3 and divide both sides by 5. right? We're essentially just taking that fraction and flipping it on the other side. Right? So now we have x is 80 times 3 over 5. Oof. Okay. And 80 times 3 is 240, so x is 240 divided by 5. X is 48. Nice. Yeah. Over. So technically, right, to move this 5 over 3 from this side to this side, you can break them up if you want and say, well, I have to multiply both sides by 3, and then I have to divide both sides by 5. So when it moves over, it just does a little switch.
You have to pull
Yeah.
same thing, but I think
No, you don't have to pull it out. I just thought it might be easier to look at with just the numbers. But if you're okay with leaving the x there and just merging them, that's fine too. Yeah, cool. Any other questions about that? Great. So what were we doing? Feels like a while ago. Okay, so the x at this intersection, this point of intersection, we're saying is 48. Right? Looks reasonable, right? And so now we can use this 48 to solve for y at that point. Right? Don't worry. Like I said, this is a big question, right? But it also covers basically everything that we've done so far. You will absolutely see this on the test. It's like a super powered question. Exactly. Right, so we have two options for finding y, right? I'm going to use equation 1 because it's a little bit nicer. Who likes fractions anyways? Not I. So C is at x equal to 48, just to make a little note of what we were actually doing here. Right? Now solve for y, right? Using either 1 or 2.
you would always have to use one and the other.
No, it'll be true for both. Because the point of intersection is the only point where they're equal to each other. Right? So from equation 1, y equals, what is it, 180 minus 2x? We have y is 180 minus 2 times 48. Thank you. 180 minus 96. 180 minus 96. All that to say that C must be at 4884. Now we get to solve for D. Solve for D, right? D is the intersection of, let's scroll through here, of equation 1 and the x-axis, right? The x-axis as a line, right, is where y equals 0. So now, just as a fact, y equals 0, and y equal 180 minus 2x. So it's way nicer to solve for, right? Because instead of those two lines intersecting, right, we have line 1 and y equals 0. The intersection of 1 and the x-axis. And the x-axis is just where y equals 0. Says a fact. So we have line 1, y equals 180 minus 2x. And I'll call it line 3, y equals 0. We want to find the intersection of these two lines. That's a little bit better, right? Now we just have y equals 0. So same thing. Substitute, I'll say 3 into 1 or 1 into 3, it doesn't matter. So then you get 0 is 180 minus 2x. And I'll finish here, solve for x. So getting x to one side, I'm going to add 2x to both sides to get rid of that minus. So I get 2x is 180. X is 180 over 2. So x must be 90. Depends on how you drew your line. But here, right? Now we know that when x is 90, right? That looks reasonable. Okay. Y is 0, that's point D. Right, so way less work than the other one. There's going to be at least one where there's a lot of work to find the intersection, and then the other few will hopefully just fall into place. Right.
So it's like super important for you.
Yeah, but like I said, I'll give you the grid so you'll have something structured like this, right? Otherwise, yeah, it won't work.
I'm like, mine's at least 110.
Yeah, so that is why I give you the grid, right? Because it makes a big difference. So then D is at 90, and we already said that y has to be 0, right? That was one of the lines that were intersecting. Right? Oh, but wait, there's more. Okay, so making a list of our intersections. We have A, B, C, D. A is 0, 0. B was 0, 100. C, we decided, was 48, 84. And D, we decided just now, was 90, 0. And again, our profit function hasn't come into play until now. So here we know that the profit was, what was it? X plus 1.2y. Great, thank you. Cool. So let's plug away here. 0 plus 1.2 times 0. I'm gonna hazard a guess that it's 0. 0 plus 1.2 times 100. 20. 48, right? X is 48 now. Plus 1.2 times 84. Can't remember. 148.8. talking money, so I did 2 decimal places, but it doesn't matter. And then 90 plus 1.2 times 0 is 90. Whoo! Well, it was all worth it because our maximized profit is 148.80. Nice. So then we conclude, therefore, the profit is maximized at x equal to 48 and y equal to 84 with a profit of 148.80, right? Whatever units, we could be talking thousands, millions, billions, whatever, right? Or just $148.80. Okay. So that's a lot of work, right? But we've seen it all before, but this is the first time that we're bringing it all together, right? So there's a lot of steps, and like I said, it will be on the test. Yeah. No, if I give you units, then great if you use units, but I don't really care about units. Yeah. In real life, it's important, but for here, I'm just looking at, do you understand the math, right? Cool. So needless to say, we don't have time to do another example because we have some other steps that we need to cover. Was that a question or no? Oh, it just looked like half into a question. No, it'll be a list of restrictions like that. No, just the. Let me scroll up here. Because one of those is the profit function, right? Because here was the question. So I have to give you the profit function, and these are your restrictions. So these are the ones you have to map and find the intersections of, and then you evaluate the profit. Ooh. All right. So, in the interest of time, I was going to explain some very brief calculus, but I'll just skip to what you need to know, okay? Because there's another way that we could maximize a profit function. Okay. Same thing, just different way of doing it. Okay. So we're starting chapter 3. Oh yeah, any other questions about that big mumbo jumbo? Linear programming? Yeah.
Because it's so long, like if we are going through, but like you mess up a number and it carries on, and like you get to a point where like, let's say it's 48, let's say we got like 52. So
yeah.
We're gonna get like part marks for like.
Yeah. So what I do is I just follow through what you're doing. So I will deduct, a mark depending on how big of a mistake it was, right? Was it mathematical? That's worth a lot of points off. Whereas if it's just like a typo or whatever, like something happened, and that's why you want to show your work, right? For me to be able to follow and say, oh, I see what happened here. No big deal. Half a mark off. And then as long as you keep going, and because how are you supposed to know that you did it wrong, right? And so then I just follow through. So that's why you want to really make sure that you're showing your work so that I can follow through and make sure you keep all your marks. Yeah, but that's a really good question because that's important. Yeah. We all want those marks, right? So chapter 3, really big topic here, business economics. section 3.1 is called the basics. It's really an introduction to calculus. We don't need it for the rest of the term as far as I can remember. So it's just like a weird little add-on that we have to kind of throw in. But what's nice is that once we finish this section, then we settle down, right? And we start talking about real topics. Yeah, yeah. Well, and the final, yeah. But yeah, so it'll be on test 1, and then we can just kind of focus our skills. Okay, and so there's a bunch of stuff that we don't really need. I'm gonna try my best to cut some stuff out. Who here has taken any calculus? Cool. Okay, don't worry. We're gonna do kind of fake calculus. Okay. So the first course of calculus is on derivatives, okay? And the derivative of a function is just the slope of the tangent line. The tangent line, what's the tangent line? The tangent line, so say you have a function, a curved function like this. At any one point, the tangent line only touches that one point. Okay, so we need to develop some terminology, but like I said, just hang tight for this class, and then we'll I'll show you how to use it, and then you'll know, and then we don't have to worry about it, right? So, the derivative of a function which we denote f of x, is the slope of the tangent line at any value of x. Okay. So basically, it gives a function for finding the slope of the tangent line. For finding the slope of the tangent line. Okay. So just as a quick little example here, if we have our x and our y, and we have some f of x, not a straight line anymore. Okay. Then at some point here, our tangent line only touches that one point, right? So it's a straight line. So each point on f of x has its own tangent line, right? And it's going to be a straight line, and it's just going to follow the curve, right? And so, and it's a straight line, so it's going to have some slope, right? And so this here is the tangent line. Okay. Why do we even care about this in the first place? We're trying to maximize a profit function. What if we have a non-linear, so not a straight line, profit function that looks like maybe like this? Okay. We need to be able to maximize the profit of this type of profit function. Okay. We use the fact that, well, if we look at this here, then we see that at the highest point, we have our maximized profit. Right? I think we can all agree. This happens if there's a monopoly. Okay. So it's a special case, but it's still something that we have to deal with, right? And so we have some increasing profit up to a certain point, and then it starts kind of dwindling, right? And the more we produce and the more we sell, we actually make less profit. Can't think of an example right now, but I can show you how to find the maximized profit. Okay, so at this highest point, right, the slope of the tangent line, the slope, remember, is the rise over run. Right? So the slope of the tangent line here, there is no rise, right? Because it's completely horizontal. And so the slope at the highest point is 0. Right? So at the maximized profit, the slope of the tangent line is 0. Okay. So what we do is we find the derivative of the profit function, right? The derivative is the slope of the tangent line. And then we set the derivative equal to 0. We force it to be 0, right? And then we're able to solve for the value of x, right, where the slope of the tangent line is 0. That's your maximized profit, right? Output of x. And then we can solve for the actual profit at that point of x. Right? So, we need some notation, right? So we denote the derivative of f of x as f prime of x. We denote the derivative of f of x as f prime of x. Right? And you're going to read it as, read f prime of x. Or the derivative of profit of x is profit prime of x. Right, so we just throw that little prime in between to indicate that we have the derivative. If you've taken calculus, then you'll be relieved to hear that we will only be taking derivatives of polynomials. So that's nice. Okay, so we will only need to take the derivative of polynomials. Okay. What's a polynomial, you ask? Oh, well, we've seen some before, right? For example, a polynomial is something like f of x is 3x to the 4 plus 2x to the 3 plus x squared plus 1. Something like that. Okay, but in general, right? Or in general, a polynomial has the form, call it p of x, polynomial, doesn't matter. A sub n times x to the power of n, right? Because we could have a coefficient, right? The a sub n is just the nth coefficient, right? It's just a placeholder, okay? But the n could be 100, right? So then we have x to the 100, x to the 99, x to the 98, et cetera, right? So in theory, we could have these as large as we want. I think we'll max out at 4, right? 4th degree polynomial.
What is a sub n? Sub n, why is that?
It's just to indicate that it's the coefficient for the power of n. So, no, but like I said, we're gonna do this. I'll show you how to do it. It's not gonna be that bad. Just bear with me. Okay. Yeah. So a sub 4 is 3 in that f of x. Because the n is the power, right? So x to the power of 4.
Oh, so it's
Right.
like saying that the exponent also applies to the numbers.
It's just saying that each of the x and the exponent has some coefficient.
Oh.
Right. And it's just a way to name them all. Oh, okay. We'll keep going. Don't worry. It's going to sort itself out. I promise. Okay. So then the next term, I'm scared to write the next term, but we're going to do it anyways. A sub n minus 1 times x to the n minus 1 plus, and then it keeps going to finally a sub 1 x. Technically, x is to the power of 1, right? Plus finally a sub 0, right? Which is just the term on its own, if there is one. Okay. All right. And its derivative p prime, of x the derivative now, okay, I don't actually like this stuff, but in my class yesterday, I kind of wanted more of this stuff, so I can't win. But I like to imagine just giving my function a bump from the right. So I just give it a shove. And what happens is that each of these powers falls down and multiplies the coefficient. And so each of these fall down, okay, from the x. And in doing so, the power is decreased by 1. Okay. So in general, let's do it in general first, and then I'll show you. It's going to end up looking like this. So the derivative ends up being a sub n times n times x to the power of n minus 1. Right? Because the power is now decreased by 1. Right? Plus a sub n minus 1 times n minus 1 times x to the n minus 2 now, right? Because it was at n minus 1 minus 1. Plus all the way to a sub 1 a sub 1 times 1 technically, right? But I'm not going to write that in there because I want it nice and clean. But I will add the technically plus 0. The derivative of a constant is 0. Okay. Derivative of a constant is 0. Okay. I wouldn't memorize this. I just wanted to lay it out so that when I say shove it from the right, you've seen it. Okay. But let's just get to the example, shall we? Let's say that f of x, what was that? 3x to the power of 4. Let's just steal the one that we have here. 3x to the power of 4 plus 2x to the 3 plus x squared plus 1. Okay. All right. The derivative f prime of x, right? You're going to imagine just giving that function a bump, right? And so now you have 3 times 4, right? That power is bumped down, right? And it's multiplying the coefficient that was already there. Times x to the power of 4 minus 1, right? I just think of it, when it gets bumped down, it decreases by 1. Yeah. Plus 2 times 3. Oh yeah, but I'm just showing. Yeah. Yeah. You can go straight to 12x to the power of 3 if you want. But for I just want to, just so things don't just come out magically. Okay. Times x to the power of 3 minus 1. Plus 2x, right? To the power of 2 minus 1, technically. Plus, but the derivative of a constant is 0. That's right. Okay. Cool. So if we simplify this, we get 12x to the power of 3 plus 6x squared plus 2x. That's it. Congratulations. You can take the derivative of a polynomial. Okay. So now, right, to maximize the profit function, we set the derivative equal to 0 and solve for x. So in this case, right, we would say, okay, then 0 is 12x to the 3. Oh, I need a better example. I'll use the one I have here. Example 77. So this is what you can expect to see and have to deal with, right? So you tell me if it seems reasonable or not. Let f of x be negative 5x squared plus 250x minus 500 and maximize f of x. That's the question. All right, so on the test, you would see something like that, right? And so you think, oh, okay, no restrictions. I have to maximize this function. Great. I'm going to take the derivative of this, right? Set it equal to 0, solve for x, use that x to evaluate f of x. Okay. Exactly. And then that's your maximized f of x. Okay. So I'll outline them as little steps here. All right, so find the derivative. F prime of x is, do we think we can handle this? Negative 5 times 2x plus 250. And that's it. No.
Okay. That last number that's not attached to a variable just by dropping the rest of the exponents.
Yeah, because technically it's times x to the power of 0. X to the power of 0 is 1, but when you bump down, that power of 0 goes away. So that's the one that's being multiplied technically by x to the power of 0. Yeah. So it just goes away. So taking the derivative simplifies things, right? So now we have negative 10x plus 250. Step 2, set the derivative equal to 0. 0 is negative 10x plus 250. I'll move the 10x to the left-hand side. 10x is 250. I'm almost there, so just hang tight. X is 25, skipping a step. I think we're all okay. We're all on board. Step 3, right? Evaluate f of x at x equal to 25, right? Because we decided that that's where the profit is maximized, or f is maximized. So f of 25 is, I'll steal it from here, negative 5 times 25 squared plus 250 times 25 minus 500, which is 25 squared is, so negative 5 times 625 plus 250 times 25, 6,250 minus 500, 5 times 625, oops, 5 times 625, negative 3125 plus 6250, scrambling my numbers here, minus 500, puts us at plus 6250 minus 500. I get 2,625. So f of x is maximized to 2,625 at x equal to 25. Done. With some practice, I think you'll start to like these questions. Good work. Yes. As much calculus as we do. Yeah, this is it. Have a good weekend, guys.
I don't understand at what point this becomes calculus versus regular math.